So good morning, student, and I welcome you back to the fourth lecture of this chapter, that is the optical detector. So recall what we learned in the previous three lectures. It is about the optical photodetectors, the performance of optical receivers, its types, and coherent and non-coherent detections. So in today's lecture, we will learn about the sources of noises in the optical receiver and its effect. So as I said, we finished with the first two units, and today we will be seeing the noise, the related terms video effect, and its effect on the receiver performance. These are the objectives, learning objectives. So we will be able to list and describe various types of sources in noise. Noises in photodetectors, their significance in signal to noise ratio, then the optical receiver structure and performance analysis with respect to signal to noise ratio and bit error rate. So let me explain you why this topic is so important, why noises are so important in the receiver's performance. So if you recall from the transmitter, transmission system, or even the photodetector operations, one thing is clear: the powers or the signals which are present over these systems are already very low value, and when it transmits over a long distance and reaches at the receiver, it gets further deteriorated. So what happens? The noise becomes comparable with the signal levels, and the chances of getting affected are very large in the optical receiver. So it is very important to consider the noises which are present in the optical receiver while designing it. So another performance criteria, as you know, we generally use the digital receivers. And in digital receivers with such high data speeds in the gigahertz per second, the data which is coming to it is at very high rate. So one cannot analyze the noise with respect to every single bit coming to it. So we have to consider a group of bits, and generally we consider the the average error probability over here. So this is a basic understanding why noises are very important in the optical receivers. And for any receivers, noises are always important because receivers' job is to produce the output with high fidelity. And these are the noises which comes from external resources or maybe at the component level, always affect by the signal. So in any receiver design, noise consideration is always important. So let's have a look at the sources of noises which are present in a typical optical receiver. So as seen over here, we have the photodetector, that is the front part of any optical receiver, followed by the electrical circuits, the amplifier, and so on, which is made up of our electronics components such as resistors, amplifier, and so on, transistors. So let's have a look at from all these where the noise is generated. So we will start with the incoming signal. Now what is the incoming signal to any optical receiver? So the signal that comes to the photodetector is a light signal from the optical fiber. And now you know very well, light is made up of what? Photons. Photons are nothing but discrete packets of energy. This is somewhat like the action of raining and coming of the light. So you have seen when it rains, the rain is falling not continuously. There is not a continuous water that is falling, but rather it is in the form of raindrops. Similarly, over here on the similar analogy, we can imagine the light, that is energy in the form of H, is not continuous, rather it is a statistical process, and this also creates a type of noise that is known as statistical noise, or the noise generated because of the statistical nature of the light and fluctuations. We get this noise is also called as quantum noise, which is mostly modeled using a Poisson fluctuation process. Then it comes to the photodetector itself. We studied in the second lecture the photodetector operation principle and its structure and its fabrication process. So generally in any photodetector, depending on its fabrication process, the materials used into which it decides. It's one of the important performance figure, and one of the figure which I have explained is the dark current. This is the current flows in the photodetector in the absence of the light falling on it. This is due to some carriers which are generated because of room temperature, the thermally generated electrons or carriers. And the other next source of noise is the thermal noise, which basically comes from any resistors which are used in the circuit, which you know from your second year. And the last one is also which comes from the transistor action. So depending on my amplifier, how it is designed and so on, the some noises are present in the amplifier. Of course, the amplifier noise or photodetector noise, dark current are control noises. Depending on the fabrication system and so on, one can control, minimize these noises. But as far as photon noise is considered, this all depends on what light is coming to the photodetector. So some of the noises are very significant and cannot be controlled beyond certain level, and hence it affects the signal to noise ratio of the receiver. So let's see the definitions of these noises which are most significant as far as the receiver, optical receiver is concerned. So a thermal noise, you might be knowing, this is a spontaneous fluctuation due to the thermal interaction between the electrons and the magnetic ions in a conducting medium. And this is prevalent in any resistors at the room temperature. And this noise can be defined as I squared equals to 4 kTb upon R, where K and T are Boltzmann constant at room temperature, and B represents the bandwidth over which this noise is considered, and R, of course, the resistance value of that resistor across which this thermal noise is calculated. Then comes the dark noise. Now, we know very well that what is a dark noise. So, it can be written as 2 into E into beta into ID, where of course ID is the dark current. And this noise, as can be seen, is proportional to the dark current. It can be minimized, as I said, by careful design and the fabrication of the detector. Here comes the next noise, quantum noise, which I explained you. It is particularly based on the discrete process of the photodetection in the photodetector due to the photonic nature of the light. So signal emerging from detector is dictated by the statistic of these photons which are arriving to it. Hence, the statistics of monochromatic coherent radiation arriving at the detector follow discrete probability distribution, and one can define the effect of quantum noise by defining it in the form of the current produced by a quantum process, and it is equal to again 2 into E into beta into IP, where IP is a photocurrent generated across the photodetector based on this discrete process. And with these three dominant noises in the optical receiver, now I can define a very important term, that is a signal to noise ratio. So it is the ratio of the power, signal power, that is the incoming power, uh, divided by the sum of all these noises, where n can be considered as the factor. And this signal to noise ratio, from your knowledge of the analog communication, is very important considering the analog system. So when you talk about the optical communication system which are analog, we generally refer signal to noise ratio. But if it is a digital receiver, digital optical receiver, instead of signal to noise ratio, we consider the bit error rate. Now bit error rate, you might also be knowing from digital communication that out of the received bits, how many bits have gone into error. So bit error rate uh, is very important in the digital communication system, hence in digital optical system. So we will see now the performance of a digital optical receiver and with respect to the bit error rate, not signal to noise ratio. So as I said, in digital receiver, the amplified and filtered signal emerging from the equalizer is compared with the threshold level once per bit slot to determine whether or not a pulse is present at the photodetector in that time slot. A simple way to measure the error rate in a digital data stream is to divide the number n of errors occurring over a certain time interval t by the number of pulses that is transmitted during this interval. This is called as bit error rate. Hence, the bit error rate is as I said, is the ratio of erroneous bits to the correct bits. So one can define the bit error rate as any upon nt, where any the number of error bits and nt the total number of bits which are transmitted. And D is the magnet which can be written in the form of this. So to compute bit error rate at receiver, we have to know the probability distribution of the signal at the equalizer's output and typical error rates for optical uh, communication receiver which are fixed by telecom regulatory system that ranges from 10 raised to minus 9 or 10 raised to minus 12 bit error rate. Remember, this is our benchmark. So bit error rate should be less than this. Means there has to be less number of errors in my uh, optical receiver. So error rate depends on the signal to noise ratio at the receiver. Let's go through a small brief understanding of what is being said in this previous slide. So as it is said, the bit error rate depends on the probability distribution at the equalizer's output, and it depends on uh, how the signal detection is done. So as can be seen over here, this is my signal, original signal, a square pulse that is transmitted, and because of noise addition, the signal may get distorted. So one can see the signal corresponding to bit 1 level 1 and the signal corresponding to bit 0 level 0. Now at the receiver, what's being done to detect the signal, a threshold level is fixed up, and this threshold level generally is the mid value of these two levels. Suppose this is plus 5 and this is minus 5. It is symmetric distribution we have called. So threshold level will be considered at 0. And with this threshold voltage in the optical receiver, detection is done. So with respect to the threshold voltage, the signal which is coming, its probability is compared, and depending on the value in this probability density function, whether it is above the threshold voltage or below the threshold voltage. If this will be above the threshold voltage, obviously this will represent level 1, and if it will be below the threshold level, that will represent bit 0, and hence this is how the signals are detected. One thing I would like you to notice that these probability density functions, if you see the weight of this is asymmetric. Why is it so small? Because the upper probability density function represents a signal that is received when the bit 1 is transmitted, and the lower one represents the probability density function when bit 0 is transmitted. And if you see, the probability distribution functions are not equally distributed. I want you to understand this very well. Now, this particular probability density function, when bit 1 is transmitted, is actually somewhat like when there is a light present. Recall in digital communication, I told you, when my input information signal is bit 1, that time in the modulated output light pulse is present, and if it is bit 0, the actually the light source is switched off and no more light pulse is present. So you can link now to this concept that if the bit is 1, in the modulated output a light pulse is present. A presence of light pulse means what? Presence of photons, and this is linked to the statistical noise. So if bit 1 is transmitted, means what? It is accompanied by the statistical noise because photons are present. But if we are transmitting light 0, and in the very simplified, in a very basic this modulation scheme, Bit 0 corresponds to no pulse. No pulse means what? There is no light energy present, means no photons are present. So no question comes of the presence of statistical noise. And this is the reason, student, this particular signal corresponds to bit 1 gets reduced in its amplitude because here more noise is present because of the presence of light. But here, because of the absence of light, the noise effect is less and hence we get a better signal. So I hope you understood the reason for having the difference in the probability distribution functions. So with this understanding, we can define now the probability here, error probability function when bit 0 is transmitted and detected as bit 1, or when a bit 1 is transmitted and detected as bit 0, and which can be obtained by considering how much it is above the threshold voltage or below the threshold voltage. Let us take an example. On my transmitter side, I am transmitting a signal 1, and uh, during the transmission or during the detection processes, the noises got added into it, and at such a level so that my signal level has fallen below the threshold voltage. Now, actually, I have transmitted bit 1, but the signal level because of noise has gone below the threshold voltage. The bit 1 will now be detected as bit 0. So this will be my area over which the error probability will be calculated for bit 1. So you will see the integrations, the P1, the error probability function when bit 1 is transmitted, the integration will begin from minus infinity to this threshold voltage. And if the opposite case is considered, if bit 0 is transmitted and because of the significant noise effect into it, if the level in the received signal goes above the threshold voltage, it will be detected as bit 1. And now I can calculate the error probability for this error in the form of the lower limit, the threshold voltage, and upper limit plus infinity. With when bit 0 is transmitted and it is considered received as or interpreted as bit 1. So with this knowledge of the probability density function, now how the signal decision is done with respect to threshold voltage, we understood the error probability function for both the bits bit 0 and bit 1, and now I can write the expression for combined error probability, that is equals to half of the bit 1 error probability or the error probability for bit 0 and 1, because it is a binary system and we will have the bit 1 and bit 0. So probability of error assuming equal ones and zeros, as I said earlier, becomes this, and the probability error functions for individual are defined. So depending on the noise variance at on-off levels and the threshold voltage, the threshold voltage VTS that decide that decides the detection process, the decision efficiency, and can reduce the error probability. So it's very important to decide the level of the threshold voltage. Generally, student, it is kept midway between. But as I explained, because of asymmetric here distribution, the threshold level can be arranged by lots of trials and errors. So here further we will derive the expression for bit error rate. So simple estimation for bit error rate can be calculated by assuming a equalizer output, which is a Gaussian distribution. So let the mean and variance of Gaussian output for pulse 1 be on and sigma square, and for the bit 0 be off and sigma square off. Understand, these are the mean and variances of this Gaussian output of the equalizer, which is basically uh, giving us this decision, taking this decision and giving us the output whether bit 1 or bit 0 based on the coming signals. So being it is Gaussian in nature, we are considering two of its parameters, the mean value and the variance for bit 1 and bit 0. With this notation, if the probabilities of 0 and 1 pulses are equally like, the bit error rate of the error probability P can be written as. So here I can write the bit error rate in the form of a complementary error function uh, as in the second expression half of in the bracket 1 minus error function of q upon root 2, that is equals to 1 by square root of 2 pi into e raised to minus q square by 2 upon q, where what is q? Q basically represents a quality factor. And why this factor is named as quality? Because you will see bottom, this particular quality factor is written in the form of the value of the threshold voltage, the mean value of the bit 0 or the mean value of the bit 1, and the variance. So depending on the variance means what? How much noise is present. So how this pulse is dispersed, whether it is narrow or wider, that will define my variance. And the mean value is how much is the value into Q. So based on these two parameters, this quality factor can be expressed, and by simplifying it in the expression of this error function, the bit error rate can be expressed in terms of this quality factor. Here is it is explained the variance and the values of the mean value and the for the bit 1 and bit 0 and threshold level. So you can see if I shift the threshold level up or down, obviously this is going to affect the decision, and chances are that the decision circuit may end up with more errors. So this is very critical deciding the threshold level. It should be such that there should be less number of errors in detecting the bit 1 and bit 0. Also, depending on how much is my mean value, so add the variance into it, that will affect my quality of detecting the signal. So student, the quality factor is all dependent on how much is the threshold level set and the mean and variances of the pulses corresponding to bit 1 and bit 0. And this is how the bit error is defined. Actually, there is a big derivation behind this bit error expression, but here, as it is not in the scope of your course, I have exempted skip those steps and directly provided you the expression for bit error rate on the and qualitative explanation and relation to the this bit 1 and bit 0 variance and the mean value and the threshold value. I hope you understood this explanation and you could relate it to the bit error rate. So bit error rate is dependent on a quality factor, and quality factor in turn depends on the selection of threshold voltage and mean value and the variance, where variance we studied is different in the pulse for bit 1 and bit 0, that is indirectly dependent on my noise, that is the shot noise or my thermal noise. So this is how student, if noises will be less, obviously the variance and the mean value will be less affected, and more number of bits, the quality will improve, and there will be less chances of the decision circuit to give erroneous bits. So this is the way you have to link the expression of bit error rate via quality factor through these parameters to the bit 0 and bit 1 and the noise added into it. So with this understanding, now we can look at the this characteristic plot for bit error rate. So you can see in the left hand side diagram, there is a plot for the bit error rate with respect to the quality factor. So as I said, as quality factor will improve, what should happen? There should be less number of errors in the system. Hence, you will see the bit error rate goes on reducing with the increased quality factor. And this is where you will see the quality factor depending on this, the bit error rate is bit error rate is calculated. Now, as I told you, for optical communication system, over so many years observation, the value which is set by the telecom, this optical regulatory system is 10 is to minus 9. Now, for 10 is to minus 9, somewhere this value falls. This is where the 10 is to minus 9. If I consider this point and then try to find out what is the quality factor corresponding to this bit error rate, it is somewhere around 5.99. So if I'm designing a quality factor here in the optical communication system, so that its bit error rate should be 10 is to minus 9, or I mean more than that, I should have a quality factor around 6. And quality factor, as I said, depends on this threshold voltage, and of course noises to certain extents are not in our hand. So by making permutations and combinations, one can refine the designing or design it carefully to have the quality factor approximately to 6, so that error probability won't go below this value 10 raised to minus 9, and it will be always maintained above this. So there will be less number of errors. So this is how you will relate the quality factor to the bit error rate, and quality factor indirectly is related to the noisy signal to noise ratio. Here I got a small numerical for you. Let us consider for an error rate that is of 10 is to minus 9, we have found this equation of bit error rate that is given in the previous slide is this expression, and calculate the Q factor. So one can easily calculate the Q factor or can observe from this diagram, and it comes out to be approximately 6. And now we can calculate the signal to noise ratio by putting this as this 12 dB and 12 signal to noise ratio, and likewise. And here we end the with this particular chapter on optical receiver, where we learn the role of optical detector, how much it is critical, the operating principle of optical detector, various optical detectors, PI, NM, PN, then the figures of merits, those are quantum efficiency and the responsivity and adapter. Then we uh, learn the entire optical receiver operation, its types and the types of noises present in it, and how these noises effect can be considered into one performance parameter, that is the signal to noise ratio or the bit error rate, and what is the bit error rate which is set to 10 is to minus 9, and how what cares you should take in designing the optical receiver so that this bit error rate should be shouldn't be less than 10 raised to minus 9. And with this knowledge, I hope you understood this entire system and you will remember now onward with for the optical communication system. These are the books I referred for this topic, as I have already shared with you. And these are the possible questions which can come on this particular topic. So you can go through them. And this is all about the module. Let's stop over here. And the next module, that is a module number 6, wherein we will be learning the entire optical link design considering the powers, attenuation, and tuning. So for time being, let's stop and bye.